Hello again, everyone. So today we're going to continue our discussion regarding the vertical stresses in soil. So last time we discussed all about the stresses in saturated soil without seepage. That means the soil is at static case. There is no seepage happening. So today we're going to discuss about the stresses in saturated soil with upward seepage. If water is seeping, the effective stress at any point in a soil mass will differ from that in the static case. It will increase or decrease depending on the direction of seepage. So this is an example of an upward seepage. There is an inflow in here. That means nagsisip yung ating tubig pataas. And the figure shows a layer of granular soil in a tank where upward seepage is caused by adding water through the valve at the bottom of the tank. The rate of water supply is kept constant. The loss of head caused by upward seepage between levels A and B is H. So this is the loss of head. So if we get a piezometer and is put in here, yung pagtaas ng tubig will be up to this level. And the difference between this level and this level will be the head loss at point B. If we get another piezometer and we put it here, there's another water level here, and the difference between the water level here and this the water table here will be another head loss, and that is the head loss at point C. At point A, there is no head loss because this will just be of the same level with the water surface. So, keeping in mind that the total stress at any point of the soil mass is due solely to the weight of soil and water about it, we find that the effective stress calculations at point A is the total stress is equal to the unit weight of water multiplied by H sub 1. And the neutral stress is also the unit weight of water multiplied by H sub 1 because there is no soil in here. The total stress will just be due to water, and the neutral stress will definitely be due to water. And then the effective stress is the total stress minus the neutral stress. Definitely, if we subtract the two values, it will give us 0. So the effective stress at this point is 0. And then the effective stress calculation at point B is we have to first get the total stress. So in order for us to get the total stress, this will be equal to the unit weight of water multiplied by the height, which is H sub 1, plus the saturated unit weight of this soil multiplied by the height from this point up to that down to that point or point B. So that would be H sub 2. And the neutral stress is equal to unit weight of water multiplied by H sub 1 plus H sub 2 plus H, which is due to seepage. And the effective stress will be equal to the total stress minus neutral stress. If we substitute the two values, this will be equal to the unit weight of water multiplied by H sub 1 plus saturated unit weight of this soil multiplied by H sub 2 minus unit weight of water multiplied by H sub 1 plus H sub 2 plus the seepage at point B. And that is small letter h. So if we combine these two, because this is common, h sub 1, and these two terms also, we get unit weight of water multiplied by h sub 1 minus unit weight of water multiplied by h sub 1 plus the saturated unit weight minus the unit weight of water multiplied by h sub 2 because that is common minus the unit weight of water plus H. This will be cancelled because this will be 0. And we all know that the saturated unit weight of soil minus the unit weight of water is equal to the buoyant unit weight of the soil. Therefore, the effective stress is equal to the buoyant unit weight multiplied by H sub 2 minus unit weight of water multiplied by the seepage, which is H. So, in order for us to get the effective stress at point C, we need to know what is the value of this H here, the head loss here. So, we know that the hydraulic gradient is equal to H over L, which means that is the head loss or the difference between two water level over the length of the soil. So in this case, the hydraulic gradient is equal to H because this will be the difference between the two water level over the length of the soil is H sub 2. That's why this will be the hydraulic gradient. In order for us to get the height of the seepage at point C, we have to perform direct proportion. So, by direct proportion, h over h sub 2, this is h, over h sub 2 is equal to h1. This will be h1 first. Let us first label this as h1. And this will be h1 over z. What is z? This is the length of soil from A to C. So, in order for us to get H1 or H sub 1, we transpose and we get H sub 1 is equal to H or the seepage over H sub 2 over multiplied by Z. That this is the value here. That's why this will be H sub 1 in order for us to get the seepage at point C. So yun yung ipa-plus natin para magkukuha tayo ng neutral stress. Okay. So to further discuss, in order for us to understand more, let us solve the effective stress at point C. So the effective stress at point C is equal to total stress minus the neutral stress. So we have to first get again the total stress. So the total stress is equal to the unit weight of water multiplied by H sub 1 plus the saturated unit weight of this soil multiplied by Z. So that would be the total stress. The neutral stress is equal to the unit weight of water multiplied by H sub 1 plus Z plus the seepage at point C is equal to H sub 1, which we already solved earlier. Therefore, the effective stress is equal to the total stress minus neutral stress, and we combine the two equations. So, unit weight of water multiplied by H sub 1 plus saturated unit weight of the soil multiplied by Z minus the neutral stress, which is equal to unit weight of water multiplied by H sub 1 plus Z plus small letter H sub 1 or the seepage at point C. So this will give us unit weight of water multiplied by H sub 1 minus unit weight of water multiplied by H sub 1 because we already combined this. We distributed first this and combined this and then plus as Z as common between these two. So saturated unit weight of the soil minus the unit weight of water multiplied by Z minus, this will be just the remaining term, unit weight of water multiplied by H sub 1. And therefore, the effective stress at point C is equal to the buoyant unit weight of the soil multiplied by Z minus unit weight of water multiplied by H sub 1. And we already solved the value of H sub 1, which is equal to H over H sub 2 multiplied by Z. Okay. How about for the downward seepage? So, in this example, may outflow naman siya. So, seeping out naman yung tubig natin and naka-open yung valve dito. So, ibig sabihin, pababa din yung ating seepage. And this will be the seepage at point B rather, and this will be the seepage at point C. This will be the seepage at point C. This one, this one. The difference between this water level and that. That's why that is the water level. Okay? So, the effective stress at point A is equal to the total stress minus the neutral stress again. So, the total stress is again the stress due to soil and water. So at point A, the stress is just due to water. So this will be equal to the unit weight of water multiplied by H sub 1. And also, the neutral stress is equal to the unit weight of water multiplied by H sub 1. Therefore, the effective stress is just equal to 0. Again, the hydraulic gradient is equal to H, the seepage at point B, over H sub 2, the length of the soil. So the seepage is H is the difference between the two water levels, and the H sub 2 is the length of the soil. So also to get the height of seepage at point C, in order for us to get this one, let us again denote this as H sub 1 first. So by ratio and proportion, this will be H over H sub 2 equals H sub 1 over Z. This will be the length of the soil at point C. Therefore, H sub 1 is equal to H over H sub 2 multiplied by Z. That gives us the value here. And then, for us to solve the effective stress at point B, we need to get the total stress again. So the total stress is equal to the unit weight of water multiplied by H sub 1 plus saturated unit weight of this soil multiplied by H sub 2. So from the down to that point. The neutral stress is equal to the unit weight of water multiplied by H sub 1 plus H sub 2 minus H. So we have to subtract the seepage in downward seepage. So in upward seepage, we have to add. In downward seepage, we have to subtract. So combining, the effective stress is equal to the total stress minus neutral stress. Therefore, this will give us unit weight of water multiplied by H sub 1 plus saturated unit weight of the soil multiplied by H sub 2 minus the unit weight of water multiplied by H sub 1 plus H sub 2 minus H, which is the seepage at point B. So, combining again the terms, this will give us unit weight of water multiplied by H sub 1 minus unit weight of water multiplied by H sub 1. This will be cancelled. This will be 0. And combine these two, unit weight, saturated unit weight minus unit weight of water, because there is H sub 2 as common, minus the remaining term is unit weight of water multiplied by negative H. Therefore, the effective stress is equal to the buoyant unit weight of the soil multiplied by H sub 2 plus the unit weight of water multiplied by H. Then, we calculate the effective stress at point C. In order for us to get the effective stress at point C, the total stress is equal to the unit weight of water multiplied by H sub 1 plus saturated unit weight of the soil multiplied by Z. So the height from point A to point C is Z lang. Therefore, the neutral stress is equal to the unit weight of water multiplied by H sub 1 plus Z minus H sub 1 small letter. And then total stress minus neutral stress is equal to the effective stress. And substituting the values, this will give us this equation. And if we distribute the unit weight of water, this will give us this equation. This will be cancelled. The unit weight of water minus unit weight of water multiplied by H sub 1 plus the saturated unit weight minus unit weight of water times Z minus the unit weight of water multiplied by negative H sub 1. Then this will be 0. This will be the buoyant unit weight of the soil. Therefore, the effective stress is equal to buoyant unit weight Z plus unit weight of water H over H sub 2 multiplied by Z. Class, if the question in the problem is just effective stress, you don't have to get the total stress and the neutral stress already. As long as you know the formula and you know the theory, you can already directly solve the problem using this equation. So let us understand more of the seepage using this sample problem. So this is an upward seepage problem. And we have to consider the upward flow of water through a layer of sand in a tank as shown in the figure. So for the sand, the following are given. The void ratio is equal to 0.52 and specific gravity of solids is equal to 2.67. So we have to calculate the total stress, the pore water pressure, and the effective stress at points A and B. So in order for us to get the neutral stress, the effective stress, and the total stress, we need to first know the unit weight of this soil kasi ang given lang is void ratio and specific gravity. And we know that in order for us to solve the total stress, the neutral stress, and the effective stress, we should consider the unit weight. So in this scenario, this is a saturated soil kasi nasa ilalim na siya ng water surface. So this will be saturated unit weight. So in order for us to solve for the saturated unit weight where specific gravity and void ratio is already given, so we just have to substitute the formula using this equation. The saturated unit weight is equal to the specific gravity plus void ratio over 1 plus void ratio multiplied by unit weight of water. So we all know that the unit weight of water is equal to 9.81 kilonewton per cubic meter. By substituting the values, we get 2.67 plus 0.52 over 1.52 multiplied by 9.81, and the saturated unit weight will be equal to 20.59 kilonewton per cubic meter. So in order for us to get the effective stress at point A, we have to first get the seepage at point A. How? So we have to draw a piezometer here. I'm sorry for my drawing. And calculate the seepage at point A. So the seepage, there is water here. For example, there's water, and the difference between two water level will be H sub 1, which is the seepage at point A. So we all know that the difference between, so we have to erase first in order for you to see the difference between the two water level. So the head loss, the total head loss is equal to 1.5 over the length of soil is 2 meters, and the height from this water surface from the bottom of the water down to the point A is 1 meter. So 1.5 over 2 multiplied by 1 will give us 0.75 meters. This will be the value of the seepage or the head loss at point A. So the total stress will be equal to unit weight of water multiplied by zero point 0.7 plus saturated unit weight of the soil multiplied by 1. Therefore, 9.81 multiplied by zero point 0.7 plus substitute the value of the saturated unit weight, which is 20.59, we get the total stress at point A, which is equal to 27.457 kPa or kilonewton per square meters. So the neutral stress at point A is equal to unit weight of water plus zero point 0.7 plus 1, zero point 0.7 plus 1 plus the seepage at point A, which is H sub 1. We already solved for the seepage, which is 0.75. So we just have to substitute the value. And this will give us the neutral stress rather, which is equal to 24.035 kPa. So in order for us to get the effective stress at point A, we know that the effective stress is equal to the total stress minus neutral stress. Therefore, 27.457 minus 24.035 is equal to 3.422 kPa or kilonewton per square meters. So that would be the effective stress at point A. So to solve for this effective stress at point B, we need to solve for the total stress. So again, the total stress is equal to the unit weight of water plus zero point 0.7 plus the saturated unit weight plus multiplied by 2. So therefore, this will be 9.81 multiplied by zero point 0.7 plus 20.59 times 2. The total stress will be equal to 48.047 kPa or kilonewton per square meters. The neutral stress is equal to zero point 0.7 plus 2 plus the head loss at point B is equal to 1.5. And therefore, this will give us 41.202 kPa as the neutral stress. In order for us to get the effective stress, we just have to subtract the two values, this total stress and neutral stress, and this will give us 6.945 kPa. So that would be the example for the upward seepage. So if downward seepage naman, negative lang to and also at point A. And last topic for this discussion, so the capillary rise in soils. So, for example, the continuous void spaces in soil can behave as bundles of capillary tubes of variable cross-section. Because of surface tension force, water may rise above the phreatic surface. So, for example, ganito. Ito yung tubig. Nilagyan natin siya ng tube. So, pwede siyang mag-rise. And that would be the height of rise of water in the capillary tube can be given by summing the force in the vertical direction. So the height is estimated to be equal to 1 over d, or what is d? This will be the diameter of the tube, so the height of the rise of water. So Haysen gave a formula for the approximation of the height of capillary rise in the form C over E D10, wherein D10 is the effective size or the diameter at 10% passing of the soil. In Shiv analysis, if you still remember, E is the void ratio and C is a constant that varies from 10 to 50 millimeter square depending on the type of soil. So if you look at this one, this is the capillary effect in a sandy soil, a soil column in contact with water, and the variation of degree of saturation in the soil column. So this is an example. So approximate range of capillary rise in soils depends on the type of soil. So if the soil type is coarse sand, it may be zero point 0.1 to zero point 0.2 meters. Fine sand is zero point 0.3 to 1.2 meters. Silt is about 0.75 to 7.5 meters, and clay is 7.5 to 23 meters capillary rise. So, how are we going to solve for the capillary rise? Paano natin masasolve yung vertical stress ng lupa pag may capillary rise or may zone of capillary rise? So, look at this example. So, at point A, if we look at this one, this is the zone of capillary rise. At point A, the total stress will be equal to the unit weight of the soil multiplied by H sub 1 plus unit weight sub 2 multiplied by H sub 2. So that would be the total stress. And in the neutral stress, di ba, sa ating neutral stress, kapag without seepage at nasa taas ng groundwater table, automatic zero ang ating neutral stress. Pero iba yung sitwasyon kapag may capillary rise. So yung capillary rise natin ay nagkakaroon ng contribution sa neutral stress natin kasi nataas ng nataas yung nasipsip ng lupa dito, itong tubig dito, kaya nagkakaroon ng capillary rise dito nataas. So, the neutral stress at point A is equal to the negative degree of saturation. This will be the degree of saturation multiplied by the unit weight of water multiplied by H sub 3, the height from the groundwater table of the point wherein we are to get the neutral stress. So the height from the groundwater table of point A is H sub 3. So therefore, this will be H sub 3. So by effective stress is equal to total stress minus the neutral stress. Therefore, the effective stress is equal to the unit weight sub 1, H sub 1 plus unit weight sub 2, H sub 2 minus negative S1, unit weight of water, H sub 3. And therefore, this will be just plus kasi dinistribute. So that would be the capillary rise. Difference ng computation for the vertical stress. Yung neutral stress natin ay nagbabago kapag may capillary rise. So if you look at this one, at point B naman, let us look at the stress at point B. So the total stress is, ganun pa rin yung pag-compute natin ng total stress, effective stress. The theory is still that effective stress is equal to the total stress minus the neutral stress. Pero nagabago lamang yung neutral stress natin kasi may zone of capillary rise. Pero yung pag-compute din natin ng total stress, ganun pa rin. Even, di ba, sa seepage, ganun pa rin. So, pag may seepage lang, neutral stress din yung nagabago and also the in zone of capillary rise. So, laging titingnan ninyo yung epekto ng tubig either without seepage or may capillary rise kasi napaka-critical ng tubig sa lupa. So, at point B, the neutral stress is equal to 0 already. Kahit pa yata siya ay nasa groundwater table. Kasi 'di ba, the formula for the neutral stress is equal to negative degree of saturation multiplied by the unit weight of water multiplied by the height from the groundwater table of that certain point. So what is the height from the groundwater table of point B? That would be equal to 0. Therefore, the neutral stress will be equal to 0. So balik ulit tayo kung paano tayo mag-compute ng neutral stress kapag nasa groundwater table. Magbabago lamang ang pag-compute natin ng vertical stresses kapag nasa zone of capillary rise siya. Therefore, the effective stress is equal to total stress minus neutral stress. The effective stress will still be equal to the total stress at point B kasi nasa groundwater table siya. And at point C, still, kung paano tayo mag-compute ng vertical stresses without seepage sa point C, ganun din yung pag-compute natin ng vertical stresses kapag may zone of capillary rise pero nasa ilalim na siya naman ng groundwater table. So the total stress is equal to the unit weight sub 1 H sub 1 plus unit weight sub 2 H, this will be that, unit weight sub 1 H sub 1 plus unit weight sub 2 H plus the saturated unit weight H sub 4. And then the total and the neutral stress. So again, ang neutral stress natin ay nasa ilalim ng groundwater table magsisimula. So the unit weight of water multiplied by H sub 4 hanggang dun sa point na kinukuhaan natin ng neutral stress. Therefore, the effective stress is equal to the total stress minus neutral stress. So we just put the values. This will be the equation. And we know that saturated unit weight minus unit weight of water is buoyant unit weight. I-combine naman natin itong dalawang terms na to because H sub 4 is common. Therefore, the effective stress at point C is equal to unit weight sub 1 H sub 1 plus unit weight sub 2 H plus buoyant unit weight H sub 4. So, para mas maintindihan natin yung ating capillary rise, let us look at this sample problem. So, this is a soil profile and given the H sub 1 is equal to 1.83, H sub 2 is 0.91 and H sub 3 is 1.83 also. So we are to determine the effective stresses at points A, point A, point B, and point C and D. So if you look at the figure, this is sand, this is saturated clay, and this is rock. So sand to. Ito ay dry sand. Wala kasing sinabi na moist siya. At given lang specific gravity and void ratio. So dry sand siya. Walang moisture content na given. And in this zone is a zone of capillary rise, may given na specific gravity tsaka void ratio and may degree of saturation na 50%. Kung makikita ninyo, ito yung groundwater table natin. Tumaas yung tubig, nag-seep, kaya nagkaroon ng zone of capillary rise. And then this will be the saturated soil na kasi nasa ilalim na ng groundwater table. So, para makuha natin, again, yung vertical stresses at these 4 points, we have to get the unit weight. So, for sand, this is given ay specific gravity lang at void ratio. Again, this is dry kasi wala namang binigay na moisture content. Pag may binigay na moisture content, ibig sabihin siya ay moist unit weight ang akunin natin. But in this case, wala namang sinabi na siya ay moist. That's why we are to get the unit weight at dry state. So this will give us 2.65 multiplied by 9.81 over 1.5. And the dry unit weight of this soil is 17.33 kilonewton per cubic meter. So, we have to get the moist unit weight of this soil kasi saturated siya, di ba, 50%. So, the moist unit weight is equal to specific gravity plus degree of saturation multiplied by void ratio over 1 plus void ratio multiplied by the unit weight of water. So, we have to substitute the value. So this will give us 2.65 plus 0.5 multiplied by 0.5 multiplied by 9.81 over 1.5 equals 18.97 kilonewton per cubic meter. So this will be the unit weight of this soil. And then for the clay, which is saturated, we have to consider the saturated unit weight. So in this case, ang given lang natin is specific gravity at saka moisture content. So in order for us to get the saturated unit weight, we know that we have to know the void ratio kasi the saturated unit weight is equal to specific gravity plus E over 1 plus E multiplied by the unit weight of water. So in this case, kailangan nating hanapin kung ano yung void ratio. So the void ratio is equal to GMC over the degree of saturation. From the relationship, GMC equals SE. So by substituting the values, 2.71 multiplied by 0.42, we all know that the degree of saturation is equal to 1 even if it's not given but it's already obvious in the soil profile shown kasi nasa ilalim siya ng groundwater table. That's why this will be equal to 1 multiplied by E. Therefore, we get the value of the void ratio which is equal to 1.1382. So, makukuha na natin yung saturated unit weight. And by substituting the values, this will be 2.71 plus 1.1382 over 1 plus 1.1382 multiplied by 9.81. The saturated unit weight is equal to 17.66 kilonewton per cubic meter. So this will be the saturated unit weight of the clay. So, solve na natin yung ating effective stresses. So, at point A, if we solve for the total stress, ano ang total stress nito? The total stress will be equal to 0 kasi wala namang soil or wala namang water na nasa taas ng point A. So, this will be total stress will be equal to 0. And therefore, the neutral stress is also equal to 0 because there's no water above this point. So pag wala namang height na makukuha tayo at unit weight na makukuha, therefore the neutral stress will be 0. And the effective stress therefore is also equal to 0 because 0 minus 0 is equal to 0. Now we solve for the effective stress at point B. So at point B, the total stress is equal to dry unit weight multiplied by H sub 1, and by substituting the values, this will be 17.33 multiplied by 1.83 equals 31.71 kPa or kilonewton per square meters. So at point B, there could be two situations. One that is immediately above point B and immediately below point B. So, pag immediately above point B, kasi pwede kasing itong point B hindi na kasakop ng zone of capillary rise. Pag immediately above point B, ibig sabihin hindi na siya sakop ng zone of capillary rise. Immediately below point B, dun pa lang siya sakop ng zone of capillary rise. Therefore, kapag immediately above point B, the neutral stress is equal to 0. And if it's immediately below, this will be equal to the negative degree of saturation multiplied by unit weight of water multiplied by the height from the groundwater table of the point, and that would be H sub 2. So the height from the groundwater table of point B is H sub 2. Therefore, if we substitute the values, this will give us negative 0.50, the degree of saturation, multiplied by the unit weight of water, which is 9.81, and H sub 2 is 0.91, which is given in the problem. This will give us negative 4.46 kPa or kilonewton per square meters. So therefore, at point B, there will be two effective stresses. One that is immediately above and one that is immediately below. So the effective stress is again equal to total stress minus neutral stress. So if it's immediately above, the effective stress is also the total stress because the neutral stress is equal to 0. So this will just be 31.71 kPa. And if it's immediately below, this will be 31.71 minus negative 4.46, which is the value of the neutral stress at immediately below point B. And the effective stress immediately below point B is 36.17 kilonewton per square meters or kPa. And at point C, again, balik tayo sa conventional way of how to solve the vertical stresses. The total stress is equal to dry unit weight H sub 1 plus moist unit weight of this soil H sub 2 down to this point C. So by substituting the values, 17.33 multiplied by 1.83 plus 18.97 multiplied by 0.91 is 48.97 kPa. So the neutral stress at point C is again equal to 0 because there is no difference between that point and the groundwater table. There is no height difference. So again, the height difference should be considered if you are to get the capillary rise. So the height difference is 0. Therefore, the neutral stress is equal to 0. And the effective stress is equal to the total stress because neutral stress is equal to 0. And that would be equal to 48.97 kP. And lastly, at point D, the total stress is equal to the dry unit weight multiplied by H sub 1 plus moist unit weight of the soil multiplied by H sub 2 plus the saturated unit weight of the soil multiplied by H sub 3. Therefore, if we substitute the values, this will give us 17.33 multiplied by 1.83 plus 18.97 plus multiplied by 0.91 plus 17.66 multiplied by 1.83. Therefore, the total stress is equal to 81.29 kPa and the neutral stress is equal to the unit weight of water multiplied by H sub 3, the difference from the groundwater table, the height difference from the groundwater table down to that point. And this will be H sub 3. And this will give us 9.81 multiplied by 1.83. Therefore, this will be equal to 17.95 kPa. And the effective stress is equal to 81.29 minus 17.95. Therefore, the effective stress is equal to 63.34 kPa. And that would be the answer for sample problem regarding the capillary rise. And that would be all for our discussion today. And if you have any question, you can always ask me personally, message me through personal message in Facebook and or text me if you want, and I will answer it gladly. Thank you everyone for watching and hope you have learned something from this video. Bye.